Fantastic. So today we have Matt, who's a fourth-year PhD student here with my proposal. Previously, Matt did his bachelor's at Illinois. He also worked apparently he also worked with Blue Origin, Liquid, and Riverbed. But now he's doing his research on better inductive biases for deep learning to address the problem of modeling the dynamics of frictional contact and fluid mechanics. So, Matt, the floor is yours. I'm excited to hear from you.
Great. Thanks, Oleg. As he said, this is a talk about learning contact dynamics, but I would like to think of myself as a roboticist, and this talk is being about robotics. So, of course, the question that raises is, why do roboticists care about modeling contact dynamics? So, really, it's a couple different questions there. Like, why do we care about modeling? Why is contact the thing that we'd like to model, and why do we need to learn those models? So, modeling is important in general in robotics. Somewhat empirically, because it underlies a lot of the most exciting things that we've been able to do in the field. So here are my three of my favorite examples, one from Boston Dynamics, another from OpenAI, and another from UC Berkeley. And while the details of the methods that have implemented this parkour and Rubik's Cube solving vary quite a bit, the underlying methods follow the same design pattern, which I'll refer to as model-based control, which generally always has the same three basic steps. First, run your robot to collect some data. Typically, this is in the form of state, action, next state pairs. Second, fit a dynamics model to the data that you collect. This could be a physical model, or it could be a deep neural network, or something in between. And third, when you'd like to do control and planning on your robot, query your model to figure out what the model thinks would be good actions, and then execute them on the hardware. And a really critical assumption that's always present, no matter how you implement this, is that the model needs to closely match reality for this process to make sense at all, and to give you reliable motion in the real world. And a critical part about this, having this close match, is fitting to some sort of data. Now, depending on the setting that you're working in, and also, frankly, the expertise that you have, you could use a really diverse set of methods to do this fitting to data. If you're in a lab environment and you know exactly how your robot behaves because you built it yourself, or you have good specifications from the hardware manufacturers, you know exactly the objects that you are going to be looking to manipulate, then there isn't really that much left to learn, right? Maybe you need to know a handful of like masses and lengths, and we have plenty of ways where you could fit those to some data with least squares, or you could just break out a scale in a measuring tape. And it's incredibly reliable. But if we want robots to make sense of an entirely new environment that they need to locomote across, or that they need to manipulate autonomously, possibly in the real world with humans around them, then it's a lot easier to think about algorithms which infer the model directly from data. And a popular recent family of approaches that is theoretically flexible enough to handle a really wide array of scenarios is to learn the entire model from scratch as a deep neural network. So you take your current state, your current action, possibly a small history, put it into a network, and out you get the next state. While this is essentially infinitely flexible, depending on the architectures that you choose, we've often seen practically that we can have poor predictive performance with these models, even with quite a lot of data. And then that's not something that you have to take from me. This is a lesson that we've learned over and over again in robotics for decades, and all the different corners of our discipline. In particular, people are really focused on friction and contact as something that's really hard to model. And within that, particularly these fast, the really, really fast behaviors that happen when objects impact each other and when the robot impacts the environment, such as when Atlas's feet hit the ground here when it does a backflip. So today we're going to go a little bit further than say that contact is hard to model, and we're going to discuss two recent steps that we've made towards doing better deep learning for contact. And the first part is we're going to cover an empirical study that we did which goes beyond the what to why contact is so hard for deep learning to capture. We're going to focus on stiffness as a key underlying culprit. And also we're going to discuss how stiffness can create near discontinuities that wreak havoc on the deep learning process. Second, we're going to discuss a model to resolve these issues with a gray box method, which we call ContactNets. So it's somewhere in between pure end-to-end deep learning and system ID. And so the key insight here is that we're going to leverage the structure that exists in contact simulation to make it a deep neural network representation of dynamics and also a training process and a new loss that are much smoother and better numerical and are better posed numerically. Okay, so before we get into how mechanical stiffness causes all these issues, let's first talk about what mechanical stiffness is. In the real world, no two objects can occupy the same space at the same time. Instead, when they collide, they exert forces on each other and deform to prevent interpenetration. Conceptually, stiffness is the ratio of the inner body forces that prevent this interpenetration to the amount of deformation, which is a similar concept to a spring constant. As deformable objects are really, really challenging to simulate, common simulators like Drake or Majoko or Bullet make a crude approximation to this behavior. First, we assume that deformations are negligibly small and that objects are instead perfectly rigid and small penetrations may happen. And we instead think of stiffness as the ratio of the normal force between objects to the amount of penetration. The stiffness, which we associate with this symbol here of K, is often paired with a damping B, which can be used to control the restitution of impacts. While this approximation could be tuned to closely match reality, in practice, stiffnesses in simulation are often set to be something much softer than the real world materials that are being simulated, simply because doing so improves the numerical conditioning of the simulation process. And while this may seem benign, we argue that doing so is just as unreasonable as modeling a robot as having wildly incorrect masses or lengths. Particularly if you don't set your stiffness to be realistically high, your simulation will not capture one of the most challenging qualities of your system for controls and planning. To illustrate the difference that stiffness can make, here we examine a state update function f of a simple point mass system. Here we're giving it an initial condition, which is a height z above the ground and an initial downward velocity z dot. And we can look at a one-dimensional slice of this state update function here. On the right here, the initial velocity is not downward enough for the object to hit the ground, so it just accelerates under gravity. But if you throw it down fast enough, by the end of a single time step, you will impact the ground, and if there is no elasticity in the collision, the object is just going to come to rest. If we reduce the stiffness from this perfectly rigid case to something with a finite but very high stiffness, we see that while we don't have a discontinuity in the middle of the function here, we have a really, really incredibly high slope. And this is a really undesirable property of a system that we call numerical stiffness, which has an etymological connection to mechanical stiffness. And we can also see that if we reduce the stiffness to something lower, these really high slopes tend to go away and we have dynamics that are more smooth. So why would numerical stiffness be something that we would want to avoid? Well, in the domain of learning a model as a deep neural network, this can cause at least three separate issues that we've noticed. The first issue, which we're going to call chaos, is defined very similarly to how we define numerical stiffness as high slope. And chaos essentially says that future states are very sensitive to their current state, which almost literally is saying that the slope of this dynamics update function is very high. And a practical ramification of this is that our understanding of the current state on real systems comes from noisy sensor measurements. So even if you had a perfect model that wasn't accounting for the noise, then your noisy initial condition could give you a wildly inaccurate prediction. The second issue with F being stiff is that it appears directly in the loss that we try to do gradient descent on when we are training deep networks. Typically, we would differentiate this loss and descend it with stochastic gradient descent. And when we think about training a neural network and gradient descent, optimistically, we have some vision in our heads where we start at some point on the wall of a bowl and we're descending perfectly down to a global minimum. But in practice with deep neural networks, the optimization landscape looks nothing like this. It looks more like the Himalayas than a bowl. And it's a landscape that's riddled with all sorts of very narrow valleys that you could easily skip over, local minima. And of course, we have many methods in the literature that can handle stiff optimization problems like this. But for the most part, these methods are designed for when you have a really small number of parameters, because they're based on something that requires an order of number of parameters squared to data or computation to calculate. And we're just not able to scale those methods right now to large neural networks. So poor optimization might mean that the training set performance is bad, but what about the test set performance? This is a really important question for deep learning, especially because in deep learning, many different network architectures can fit your training data perfectly. And we have to pick one of those networks with a bias that we would call an inductive bias, based off of some idea, some qualitative idea of which model would be best. Many of these metrics can be traced back to Occam's razor, which can be phrased as the simplest explanation is usually the best. And there have been many iterations of this, maybe most famously by Vladimir Vapnik, but one very popular modern one, particularly for deep learning, is to say that deep learning is typically able to perfectly interpolate the training data and get very low training loss. And the underlying inductive bias is to select the smoothest function, which does so. The concern then is straightforward. The dynamics that we would like to be learning are not smooth. And so this bias is not correct. And we can even see this on our 1D example from just a couple slides ago. So here what we do is we collect some random noisy training data on both a low stiffness and a high stiffness setting. We repeat this tons and tons and tons of different times. And then here we show like the average and standard deviation of model predictions. And we can see that almost all of the models are very close to the real underlying function in the low stiffness regime. But as we move over to the high stiffness regime, not only is the average model farther from the real underlying dynamics, but the intermodal variance is higher. So there's something less reliable about the process as well. So each of these three issues is individually concerning, but how do they interact with each other to affect our learned models? Well, as a reminder, what we have is some finite amount of noisy training data. And what we would like is to have low prediction error at test time. And in fact, we can take that test time error and decompose it into three separate terms. The first component, which we call an oracle loss, captures the performance of a perfect model on noisy data. This term, because as stiffness increases, the underlying system becomes more sensitive to noise. That was the first problem we covered, chaos. The second term captures how the difference in performance between a perfect model and the best you could do with a learned model on the training set. And this difference is precisely what would happen if you reached a suboptimal point in the training process. And the final term here is the difference of performance at test time and training time, which we expect to get worse as stiffness goes up as our smooth inductive biases become less accurate. But deep learning is a fundamentally empirically driven field currently. So the real question is like, how much does this affect the learning process? Yeah, maybe it does a little bit, but is it something that we should actually be concerned about? So our approach to analyzing this is that we first wanted to take a look at a single system and quantify how the learning process becomes degraded if the only thing that we change is the underlying mechanical stiffness. So first we chose a single die roll system as our example of interest because for one, it's a relatively low dimensional system, so it's pretty tractable to do hyperparameter optimization to make sure that we aren't just getting poor performance because our learning rate was chosen poorly. But also because even though it's small dimensional, it has a really complex contact behavior. We think of dice rolls as being so hard to predict as they're essentially uniform random numbers. And we chose to conduct our experiments in simulation, which does have a somewhat of a negative effect because it does lessen the relevance to the real world somewhat. But also in the real world, there are endless compounding factors that we're unable to control for. And furthermore, we don't have a true model for anything in the real world, so it's hard to test how our learned models would be doing versus a true model. And here we can see a couple examples of this dice roll system being simulated in Majoko, and you can kind of get a sense of what the underlying stiffness is and the softest and the most rigid case that we've tested. So we also chose to use an optimistic principle for comparing the model performance here. And what I mean by that is that there are many other problems that we're tackling in learning robotics these days, which can include the difficulty of transferring hyperparameters across different data sets, across different problems. Or there could be a distribution shift between our training and test sets. And so instead, because we're trying to really focus in on what stiffness is doing to the training process, we've decided to make sort of everything else as easy as possible. So our training and test data sets are coming from the exact same distribution. For every single stiffness setting that we used, we individually optimize hyperparameters. So that this is essentially the best that we could possibly do on this system. And furthermore, we're going to primarily evaluate our models on single-step predictions. Long-term prediction is also a large challenge, but we found that even in the single-step prediction, we're going to see some notable effects. So at the end of the day, when we tested this, we've seen that all these three separate terms can degrade over two orders of magnitude, and we can observe that this trend over a wide variety of data set sizes, going all the way from just 50 training trajectories all the way up to 5,000 training trajectories. On the middle on the right here, we plot the performance trends as this training set increases. And what I think one of the most concerning problems is that even in a very, very high data regime on our stiffest model, which is shown here in blue, we don't see that generalization error trends towards 0. So when you add these all together to get the final test set error, it looks even more dramatic. And particularly, we note that our most stiff models, which is something relatively realistic, even with 5,000 training trajectories, it's still performing worse than even our medium stiffness model on just 50 training trajectories. So here we have some visualizations of rollouts from these models. And generally the trend that we see as we go from soft to hard, the ground truth motion becomes more and more realistic, but also the mismatch between the ground truth, which is shown in blue, the ground truth is shown in red, and the model predictions in blue becomes larger as well. And as a result, none of these learned systems were able to show a realistic dice roll. Okay, so how can we respond to these issues? Well, the first term here is independent of the training process. It's something inherent about your system dynamics. This is it's essentially the only thing that you could do here possibly is change something about the underlying dynamics of your system. So if the problem you're trying to solve is a locomotion problem, you could literally put rubber on the feet of your robot, which often we already do for completely separate reasons to make the dynamics softer. But if you're trying to solve very general problems, say in manipulation, where you're going to be interacting with possibly rigid objects, and those rigid objects are going to be interacting with each other. To some extent, you have to resign yourself to the difficulty that's inherent to the task. So what about the ones that we can change? Well, to change the training process, one option that you have is you can change the loss that you're using to be something other than naive prediction loss. If you have some structure in your model, you can add some you can think of that as adding some regularization based off of your structure. But also this could mean replacing this loss entirely. And finally, hopefully what we'd eventually like to get to is to be able to use inductive biases that smooth something other than this function f directly. And so next we're going to pivot and start talking about ContactNets, which is a model that we developed last year in our lab. And I would call this a gray box model. You know, it's somewhere between white box sysid, where you're just identifying a couple of masses, and a completely uninterpretable model. And the general philosophy that we're going to have here is we're going to take deep neural networks and combine them with the structure that exists inside physics simulators like Majoko, Drake, and Bullet. And what we would like to be able to, what we're going to do here is we're going to use the physical structure imparted on the model to construct a new loss that, instead of being based directly on forward prediction, is going to be based on obeying mechanical laws. So how can we frame contact dynamics as a smooth interpolation problem? So what we said is that deep neural networks are good at smoothly interpolating data. And the inspiration we're going to use here actually isn't going to come from some complicated mathematical structure. It's just going to come from some human intuition. So here I have a trajectory of a ball falling under gravity. And as humans, we can look at this trajectory and figure out, like, okay, so the ball falls along a parabolic arc, and then all of a sudden something happens, and the ball is all of a sudden going from traveling downwards to traveling upwards. So there must have been some sort of impact there. And then there was another one, and another one, and another one. And despite the fact that I haven't drawn any geometry of what this ball might be impacting, in our heads, we tend to see that there were 5 different points of impact and interpolate smoothly between them to assume that the ground is a straight line. And so this is exactly the intuition that we're going to use in ContactNets. Instead of trying to learn the entire dynamics as a deep neural network, we're going to learn everything about contact as deep neural networks and use the mathematics internal to simulators to turn that into a forward prediction. So specifically, we're going to be parameterizing object geometries as a signed distance function, phi. And we're going to be parameterizing the friction parameters as something that looks a lot like the same Coulomb friction model that you would be familiar with from undergraduate physics class, just a little bit more general to be able to account for varying levels of friction at different points on objects. So what is signed distance? More precisely, it's a mechanism that simulators use to, amongst other things, detect collision. So if you have 2 objects that are out of contact, so there's some space between them, the signed distance is equal to the minimum distance between any 2 points on the 2 objects. So in the left case here, we have our dice not impacting the ground yet. Phi is the distance between the lowest point on the die to the ground. When 2 objects are just barely touching on their surfaces, the signed distance is 0. And when objects are interpenetrating, signed distance is negative, and it represents the maximal penetration depth between the objects. So if you have a relatively stiff system, you know, the stiff systems are the ones that we have trouble learning right now, you can simulate that using a law that is known as complementarity, which says that either one of 2 cases has to be true. Either you have to have some gap between your 2 objects, so phi is positive, and then the force between the objects has to be 0. You can only have contact forces between objects that are touching. Or in the other case, objects are just barely touching each other, and then the force between the objects will be something that maintains that prevents them from interpenetrating. So now we can look a little bit about how this gets embedded into the structure of the simulator. So I have this block diagram here that is fairly simplistic, and it actually quite closely mirrors the structure that exists in just about any simulator you may have used for robotics. So from the current state and action S and A, what the simulator will do is it will calculate two sets of terms. The first group of terms is related to contact-free motion. This is blocked here in yellow. These are things like motor torques, inertial effects, like the Coriolis effect, gravitation. These are typically things that we know ahead of time, or something that we could identify relatively easily with our standard system ID white box processes. And the other set of terms are terms that are related to contact. And for most simulators that are simulating inelastic collisions, really this is only the sign distance and some generalization of that friction coefficient. And then what happens in the simulator is both of these two sets of terms are input to something that we call a contact force solver. And all of the near discontinuity and stiffness that is present in simulation is entirely contained in this block. This block usually contains some form of convex optimization or non-convex constraint solving problem. Usually it has some notion of this complementarity in it. And what we're going to do with ContactNets is we're going to be learning phi and also the friction parameters, and we're going to be inserting them directly into the software architecture of the simulator. And so what we've done in this case is, we have made some concessions. We're going to assume that we know some masses and gravitational acceleration ahead of time. But now the model space that we're learning is actually like quite large and vibrant. It can handle arbitrary geometries and spatially varying and anisotropic friction as well. Okay, so how can we use mechanics to provide an alternative to prediction loss in this case? Well, if we had access to contact forces directly, this would be relatively trivial. We say that the laws of physics that contact must obey says that neither phi nor the contact force can be large at the same time. One of them is always going to be equal to 0. So we could make a penalty that's based off of that we know won't be violated very much, and we could train using that loss. But the problem is that we don't know contact forces directly in many cases. Sometimes we're able to have contact forces because we have them embedded in our robots, but as soon as you're doing something like manipulating multiple objects that are contact each other, it becomes very impractical very fast to be embedding contact sensors all over the world in front of you. So to solve this, we're going to use two ideas. The first is that while individual contact forces are not available directly from the state and action data, net forces are available. We can use Newton's second law, F is equal to ma, and we can just differentiate our state, or really do a finite difference to recover the net forces over a time step. And the second thing that we're going to do is we're going to relax the idea of what the loss does. So prediction loss would say that given our current state and action, we want to definitely be able to predict the next state. And if we had access to the contact forces, we might specifically say, well, from this current state and action, under these contact forces, we should arrive at the next state. But instead, what we're going to do is say we don't know what the contact forces are, and we're going to make a lighter claim, which is that there should exist some contact forces which both cause the next state to happen. So the contact forces add up to the right net force to take S to S prime. And secondly, that those contact forces must obey the physics laws of contact. So if our model says that the the distance between two bodies is large, then the contact forces cannot be large as well. And we have some similar constructions as well that can handle friction. So this becomes a little bit of a harder problem because now we've posed evaluation of the loss itself as yet another optimization problem. But with some modern techniques from the machine learning and optimization community, we can actually transform this loss into a convex optimization problem that we can solve on the order of microseconds. And we can also efficiently differentiate this loss, so we can do gradient descent as well, just by solving a small system of linear equations. So what does this loss look like on a simple example? Here we're going to return to our really simple example of a point mass impacting flat ground. We're going to collect some data on the system and say that we don't know what the ground height is. So ZG here is our ground height. If you just took a physical simulator and then put in a ground height and asked how much how well does that simulation match the data, then you would get this blue line here with all these discontinuities in it. And in one dimension, maybe it's not so hard to optimize this. You can notice that there's some like slight slopes that will take you towards the center. Here, the actual ground height is 0. But it's much easier if you use the loss that we developed instead, which, much like this idea of having a loss that looks like phi times lambda n squared, we see something that isn't exactly quite a quadratic, but has this nice convex shape to it. So practically evaluating this, so as our first pass, while the pandemic was still raging, my co-author Sam actually set up a real world dice rolling system in his apartment. So this is actually his coffee table from last year that you see here. And so we're going to take the same dice roll example and put it into the real world. Let's collect some real noisy data and ask, does our learning method solve some of the issues that we saw in simulation? And so we're going to compare 3 different iterations. First, we're going to consider a baseline method. So this is one that we developed. This is this black box method of just mapping current states to next state. We're going to call that end-to-end. The second model we're going to evaluate is one we call ContactNets polytope. This is an iteration of ContactNets that maybe looks a little bit more like system identification, where we have a handful of unknown constants. And in this case, this is just the position of the 8 corners of the cube and body frame. So 24 parameters, give or take. And then the third thing that we're going to test is sort of the full version of ContactNets, where we're going to say that all of the frictional behavior and all the geometry in the system, we're going to learn purely as a deep neural network. So in the baseline case, we're really not able to capture this dice roll behavior qualitatively. So here we can see the real cube with the equal tags on it, as well as the model predictions from the baseline method in green. And we see that while the bulk motion is correct, and the center of mass of the cube roughly follows the right trajectory, it just looks qualitatively bad. It doesn't come to rest. It penetrates into the ground by several centimeters, and it just kind of sort of swims off like it's in quicksand. But we're able to get something that looks both looks qualitatively better and is quantitatively better if we start giving it this physical structure. And so on 1/8 of the training data, we were basically able to identify the shape of the cube and the friction to a couple millimeters of tolerance here. You can see the predictions look a lot more realistic. The cube clearly impacts the ground, and its velocity is slowed by friction, and it comes to rest. And granted, there are definitely still some major differences between the two, but this is sort of the best that you could do with a parameterization that simple simulators give to the dynamics. And it's sort of the approximation of contact in here that ended up being the limiting factor. For one, I said that we weren't doing elastic collisions, and we can see that the cube is like quite bouncy, so we are missing that effect somewhat. But quantitatively, this ends up doing about 2 to 4 times better, depending on the metric that you look at in terms of forward prediction. And now we can look at the sort of the full version of this model that's learning all the geometry and the friction as a deep neural network. And more or less, it gets to the same level eventually. This is the purple line here on the plot. It does a little bit worse, of course, because it has a lot more to learn. But qualitatively, it's very hard to tell the difference between the two. And so this is that was more or less all the past work that we've done. And we have a lot of work in the lab that is moving towards pushing this technology forward. The first and sort of obvious thing that we know is a limitation of the analysis is that we focused on quite a simple system, this dice rolling. And it can be very different practically than a lot of the real world robotics tasks that we'd like to solve. And so one thing that we're going to be doing is we're going to be taking this analysis of the effect of stiffness on deep learning and scaling up to very, very large and very complicated tasks in simulation. So for example, we'd like to do a much more realistic locomotion task. And we'd also like to take our method ContactNets and start using it in the loop in control tasks. And we'd like it to be able to manipulate and learn about objects that are much more complicated than a simple cube. And then finally, the third area of interest is to be able to take some of those artifacts of the simulator, like inelastic impact, and be able to actually use our method to extend the capability of these simulators to model more complex effects, such as restitution that is dependent on the pre-impact condition. So thanks for coming to the talk. I'm really grateful to my collaborators here for all the help that they've given me, particularly to my advisor, Michael. The work on ContactNets was with Sam Frommer. He was a CIS undergrad in the lab, and now he's moved on to do his PhD at UC Berkeley. And the analysis work was done with Mihir Parmar, who is a RoboMaster student, is now doing autonomous driving at Lucid Motors. So thanks for your time, and now I'll take any questions.
Really good talk, Matt. That was great work. So I have a question, and mostly about ContactNets. So in like I guess the deep learning and like machine learning kind of communities, like less specifically maybe focused on robotics, I know that there's been a lot of like this sort of differentiable physics, like in deep learning literature. So I know this was like kind of from the robotics perspective, so you focused on like those the comparison of like the robotics community, but with like the machine learning community, how does this compare to like other approaches out there that integrate physics in like a neural network? And also just like, are those approaches not applicable to this problem for some reason? Like how does that compare?
So I'll kind of group those into two types of methods. There are some methods that are maybe more use some like light inspiration from physics. So this is something like I mean, like that's not a bad thing, right? It's something between a deep neural network and like a full-on physics simulator, right? So interaction networks is one that I would sort of classify in that group. And with interaction networks, it captured often the sort of like light structure to physics isn't really focused on like the individual object level or link level in the robot and how those behaved. It's more focused on, how do you scale that up to larger simulations with many, many objects. But many of those methods just end up being exactly the same as just a feed-forward neural network in a case as simple as just one object interacting with a static surface. Right. And so essentially that's going to have the same performance that we saw here. And then the second type is doing something that's sort of similar to ContactNets, where you embed some learned components directly into a simulator, and then you train the simulator using just forward prediction loss, and you do something to the simulator to make sure that it's differentiable. And we've had differentiable simulators for a long time now, and in practically, while it is technically, while many of these simulators are technically differentiable, they're almost discontinuous, and so practically it's still quite a challenge. So in that sense, some of them can be similar in spirit to ContactNets, but really it's also like this difference in how we train the networks. That's a key component. And I added, at least as far as I've seen, the results on those sort of methods that don't have some sort of specialized loss function are usually actually, I don't know if I would really characterize them as deep learning, because usually it's only a few parameters, and they use one of those second order or global optimization methods that I referred to briefly before that don't really scale so well to large amounts of parameters.
Okay, yeah, no, can you transfer those things in the simulators to the real world? Like if people shown that, or is that?
Transfer what exactly?
Like the stuff you're talking about, like the differentiable simulators, if you train something on that, like can you put it on a real robot? Are there like barriers to that?
Well, I mean, in principle, all the simulators that like physics, people who do physics-based modeling in robotics, all the simulators that they like to use generally are differentiable, or at least piecewise differentiable. And a lot of like the work on differentiable physics recently in the machine learning community is using models of essentially the same form. So sometimes like that work will give you a parameterization that you can literally just dump into Mujoko or into Drake or something like that. And other times, that might not be true, but if you put in the engineering effort, you can like actually get into the open source code bases and integrate them. And we'd probably expect them to perform similarly at the end of the day.
At least as long as, or to the end-to-end method?
To ContactNets, really. I mean, ContactNets at the end of the day, it is a simulator. It's really it's identifying a system and simulating it with standard simulator math. So anything that at the end of the day is simulating with standard simulator math. If the parameterization that's underlying it is as accurate as ContactNets, the performance would be identical. The question is like, there's kind of like two halves to like the model. There's like, what is the model space, and have you found the right parameters of that model space? And for a lot of these methods, the model space is the same, and just the method of finding the parameters is different.
Yeah, it's super cool. Thanks. No, that makes sense.
Any other questions?
So I had a question. I guess so. This is sort of going back to the beginning, but at the end of your talk, you mentioned that you're interested in kind of scaling this up to more complicated locomotion and manipulation tasks. Then in the beginning, you've shown this kind of like prior work on the shadow hand, the OpenAI work or the Google work. So do you think this approach could sort of like, I guess, yeah, like what are you thinking in terms of applying ContactNet to these kind of systems? Like, do you think this is too easy, too complicated? I don't know, what's your perspective?
So maybe the easiest one to like talk about here is the Rubik's Cube example. This example does use a simulator. It uses Majoko. And it's a very, not only was like much of the like parameterization in the simulator very carefully crafted, but also they used randomization of sort of all the constants that they didn't know ahead of time, or some constants that they thought being robust to changes in would be good for the policy. And so if you're starting with using a simulator, ContactNets is really just a way to give you a good starting point, a good parameterization to shove into your simulator. But I would also add that, you know, one of the struggles there is I think they actually used 13,000 years worth of simulated data to do this. And so like there's this whole other like focus of research nowadays, which is not on like how do you get the parameters to the simulator, but once you have a simulator, how do you make it faster? And the common example these days is through GPU parallelization. And I think that's actually one of the major drawbacks of using a model that is a simulator, is that it can just be a lot more expensive to evaluate than a feed-forward neural network.
Right, so that makes sense to me, but I was actually asking about identifying the simulator parameters, because presumably the OpenAI folks did it by hand or something like that. I don't entirely know how they did it, but then the third work just trained an end-to-end deep neural network to kind of model the dynamics, right? So like, I'm curious, like, do you think your particular optimization procedure from ContactNets, like, would it be able to handle this kind of complexity? It seems that you're positive on this, given like your usual.
I think we're pretty positive on it. I think honestly, there's like quite a lot of like engineering effort that is going to have to go into scaling it up to many objects or really complicated robots. But one of the things that's nice about having this sort of physical sensibility to the model is you can really easily put in half of a known model, right? So OpenAI, as I understand it, I believe they manufactured this hand themselves, or at least they're closely involved in the development of it. And like they definitely have to know, they have all the CAD files for all the fingers. Like it's very easy when you like parameterize the entire model in terms of the physics to say, okay, here's the entire model of my hands. I don't know what objects it's going to be interacting with. I just need to learn the geometry and the frictional parameters of those objects. And so in reality, I mean, maybe not for this example, but for like the cube reorientation task, it's more or less like it's the same amount of unknowns in that case. You have a cube in the hand and you don't know that it's a cube and you don't know the coefficient of friction with it.
Yeah, that makes all sense to me.
Yeah, but like learning all that, all like the entire like structure of the hand from scratch, that would definitely be a real challenge.
Right. Yeah.
I mean, I think it's gonna be a real challenge anyway, to learn a model like that from scratch. And maybe that's why that they did not learn a model in this.
Yeah, agreed.
Any other questions?
And for the folks who are online, you can also just ask. We should be able to hear you. Or post in the chat if we can't hear you. All right, well, I guess if there are no more questions.
Thanks so much for hosting.
Yep, thanks a lot for the talk. This was really interesting. So, well, everybody knows where to find Matt, so that's a good one. Okay, well,
Thanks, Matt.
thanks, everybody.